Okay, here's a quick demo of my new QRP transmitter that I'm designing to work with my little mini SDR radio. So it's going to have some TX RX switching and mute circuitry. That's going to be right below those two toroidal inductors for the output filter. So what we have here is a little microcontroller and an OLED display and a rotary encoder to adjust our frequency, and we're using a SI 5351 clock generator to create two output square waves 180 degrees out of phase, complementary, to drive a 74 AC 240 octal buffer. Um, a few of those outputs are used for control signals from the microcontroller, and two buffers in parallel are used for each leg of the complementary drive. And then I have two little MOSFETs right there, little SOT23 MOSFETs. Uh, so it's just a simple switching amp. We've got a center tapped transformer on a little 61 material ferrite balun core, and then a sorta balun to convert the balanced output into a single-ended output. And then we do impedance matching, about 14 ohms to 50 ohms with a little L network into a symmetric pi network, 50 ohms in, 50 ohms out. And I have that set up for the 30 meter band currently. So what's interesting about this is that the whole thing is designed to run at a nominal 4 volts. So it's powered using one of these little lithium ion rechargeable battery cells, and it says 3.7 volts here. That's its voltage basically when it's discharged and all the energy has been depleted. So they'll charge up to about 4.2 volts and work their way down to 3.7. But they're small and light, and they charge it fast and have tremendous energy density. So because I'm using such a low voltage and the impedance is so low, I decided to do a push-pull design to help with efficiency. And as well, although I looked at a Class E approach, it's so tricky to tweak and optimize. This has no tuning requirements. You basically have broadband balanced transformers and then a simple matching network and a symmetric pi filter, all easy to find online or calculate very easily, which is what I did. Installed it, then it worked perfectly. And so the output of this is about 2 watts at 4 volts. So it actually draws quite a lot of current, but the battery can handle it. The efficiency is about 75%, which is very good. The MOSFETs are nothing special. They're 40-cent switching MOSFETs. They're 30 volt, drain to source voltage, rated at 2 amps, max current. An important feature is they have low output capacitance, which reduces their losses. It's under 10 puff per MOSFET. So let's look at a couple of the operating parameters here. So on the supply here, as you can see, I'm operating at 4 volts, and there's 30 milliamps of quiescent current draw simply from the clock generator and the microcontroller. And if you drive the MOSFET final output stage with no power connected, it draws about 75 milliamps to drive the input capacitance of the MOSFETs. So we'll deduct that 75 milliamps from the final power draw that you'll see when I operate the transmitter here. So I'm gonna switch hands here, and so let's go ahead and fire it up. So you can see it's drawing about 820 milliamps when it's running. And then let's look at the spectrum here. So that's about 33 dBm, and you can see the harmonics are way down. So we're looking at 50 dB down. The RMS voltage is 10.7 volts, and we can see very clean output. And so now we're up to 825 milliamps. I'm going to turn it off. So if you deduct the 75 milliamps from that total, you're looking at 750 milliamps. So that's 3 watts. And it's about 2.1 to 2.2 watts output. I'm going to change to the sinusoid here, time domain. Yeah. So let's look at that. So there's the output. So it's approaching 75% efficient. So there's very clean output you can see here. So that's pretty good, and that requires no special tuning or tweaking on that design, that amplifier. You just build it and it's going to work. So I'm going to post all my schematics and design information when I complete this thing on my blog, Circuit Salad. And I can't wait to get this thing on the air and give it a try.